Hi, so this video is going to cover lesson 2.11 in the math literacy textbook for Math 910. So this lesson you can see is on solving simple equations. And what we're going to do in this section is look at two approaches, like a numerical approach, which is probably maybe what you're most comfortable with, like using arithmetic. And then we're going to also show how we could solve a similar problem, but with an algebraic equation. And the next, so this first example, the Explorer, just tries to get us thinking about maybe having like an applied problem, like a word type of problem, and trying to figure out a solution. So you might come across trying to do this with an equation or trying to do it numerically. So I don't know, you might maybe pause the video and see if you can try number one on your own, and then I can help you, at least show you how I think about it. So you can see number one, it says Erin runs a concession stand for a high school football game. She wants the prices to be whole dollar amounts that already include a 6% sales tax, right? So essentially we want them to be whole dollar amounts so it's easy to make change, right? So when you buy a hot dog, instead of paying like $1.97 or something like that, it's just a lot easier to make change if they're whole dollar amounts. But we still have to pay sales tax, right, which is 6%. And then for each item in the table, the price for the customer is given with the sales tax included, right? So in other words, these amounts already include sales tax. So then we're asked, what's the actual price for each item before the tax is added, right? So in other words, like if we look at the hot dog item, way we can think about it is we have the hot dog price, right? And then we have to add in the tax to get the to get the total price, right, in the end, right? So when I use the word hot dog dollars or hot dog price here, I'm meaning like before tax, right? How much you would pay like without tax. So then total price, I'm using that word just to mean that's how much you would pay after tax, right? So this is pre-tax, and this price is post-tax, or with tax, right? So then you have to think about, well, how is tax calculated, right? So we would have our pre-tax hot dog price, right? And then we'd have to add in 6% times the hot dog price, right, to equal the total price, right? So I'll just use T for total, right? So this meaning that these are equal, right? I just rewrote how to actually calculate tax since we know the percentage, right? And of course 0.06 is 6%, right, just in decimal form. So this is where it gets maybe a little complicated about how do I figure out the hot dog price. So if you wanted to do this numerically, right, what you'd have to think about is this represents a 6% increase, right? I have to pay 100% for the hot dog, and then I have to add in 6% of tax, sales tax, to get me 106%, right? So this is a 6% increase, right? So in other words, if I take 1.06 times the hot dog price, this should equal the total price, right? So in other words, 1.06 times the hot dog price would equal $2, right, from the table, $2. So then, if I know a number times 1.06 equals 2. How could you solve that numerically, right? I could just take 2 divided by 1.06, right? That would give me the hot dog price. Right? So then I can come over to my calculator. Let me get out of this. Right, so we would take 2 divided by 1.06, and we come up with roughly $1.89, right, if I round to the nearest cent, right? So for the regular hot dog, the pre-tax price would be $1.89, right? And then so if you think about these, all the remainder of these would be done in a similar fashion, right? I just need to take the price in the table and divide by 1.06, because the sales tax for all of these is 6%, right? So I could, rewrite and redo my thinking about all of these, but I just need to divide by 1.06. So for the jumbo hot dog, I would take 4 divided by 1.06. So that's roughly $3.77. Right? And then for the soda, I would take $1 divided by 1.06, and that's 94 cents. Right? And notice each time that my price is smaller than what's on the table, right? And that's what we hope happens, right? Because I take this amount and then add in the tax to get the higher amount that's in the table. Right, so the pork chop sandwich, we would take 3 divided by 1.06, and we get $2.83. And then the combo is $5, so I would do 5 divided by 1.06. So we get $4.72, rounding that. Right. So then so I mentioned that we're gonna try to do things numerically and algebraically throughout this section, right? So for this, just to get us thinking, I'm gonna leave it here with numerically, right? So in other words, we didn't use any variables. We just try to think it through, and then think about what kind of operation that we needed to do to figure out the answer. But one thing that we'll find is the more complex that we get, the harder it is to do problems numerically, and that's where algebra really is helpful, right? So then the 3 kind of questions we want to focus on is, can we write a simple equation, a model, given situation, right? And then secondly, do you know the inverse operation for each given operation? And then when is a problem easier for you to solve with algebra than with a numeric approach, right? So we want to be able to answer these 3 questions by the end of the lesson. Right. So here's an example. So this problem's already worked out for us. It says that Ellie says he needs only $225 more in his account to reach the $1,875 necessary for a down payment on a car. How much is in his account? Right. So you just want to pay attention to the table. It's kind of a guiding example to help us for the future problems. So in part A in the table, we're going to solve the problem numerically, right? So you can read through this, but we're just thinking through the information and how would we, what kind of operation, like what would need to be done in order to figure out the solution. So for this one, we just need to subtract the 2 numbers, right? Because this is the additional amount he needs to reach this amount, and we're trying to figure out how much he has now, right? So in other words, we're thinking about, what he has now plus $225 is going to equal the $1,875, right? And that's my goal, right? And this is what, the additional amount that I need. Right? So that's why we're thinking about subtracting those, right? Because obviously the difference between those is going to be what I have now, which is a smaller amount, right? So that's how you can think about it numerically. And then algebraically, right, we can, maybe instead of using words to represent what we're talking about, we could use a variable and do some manipulation to solve the equation, right? So like here, I kind of already made the equation. So they're using the variable b to represent the current account balance, right? So it's also just easier to write, right? So that way we don't have to keep writing lots of words, right? So it's just easier to manipulate and work with when we have a symbol, right? So we can come up with that equation, right? Just thinking through how I did. And then the next thing that we want to be able to do is solve an equation, right? So one thing you want to remember is that we can add or subtract the same number to both sides, or multiply and divide the same number to both sides in order to solve an equation. And our end goal is to get the variable by itself, right? So kind of the steps that you want to do is step one, you want to simplify the equation if possible, right? So step one, you want to simplify. Step two, you want to get all your variable terms on one side equals, and then all your numbers, right? And if you want to be a little more technical, each of these guys are terms. So terms are like objects that we're adding or subtracting on both sides of the equation. And then a variable term is a term that has a letter in it, a variable. And then a constant term are the numbers, right? So that's what I'm meaning, just trying to break it down a little easier. So you want to get all your variables on one side and then all your numbers on the other. And then basically the third step is to divide by the coefficient to both sides. Right, and just a refresher, like if I have the term 5x squared, right, this number out in front, that's the coefficient, right? So whatever you're multiplying your variable by, right? Where like this 2, right, that's an exponent, right? So that's what I mean by the coefficient, just to review. So you want to divide both sides by that number, and then you get x by itself, right? And then maybe the fourth thing you want to do is we've already looked at before how we can check our work, right? So remember how to see if something is a solution or not. You can just plug it into your equation and simplify both sides and see if you get the same number or not. Right, so these are kind of just some general steps to solve what we call we can just say degree 1 polynomial. Equation. Right, and you may or may not know what that means, but I'm just specifying because these aren't the steps to solve every equation, but the simple kind that we're dealing with right now, those steps can work, right? So like here, when we solve this equation, notice the work is that you want to get all the numbers to one side and all the letters on the other, right? So one way to move this term over there, in a sense, is to subtract it off, right? So if we subtract that term from both sides, then this side becomes 0, so we're left with just b, right? It'd be like b plus 0, but we don't need to write the 0. And then, on this side, you get the solution, right? And then just like I mentioned, part D, we're going to check our work. So we just need to plug in our answer for B, right? So notice we just took and put it in B's place, the 1,650, and then simplify the left-hand side, and we get the same number on both sides, right? So since it's a true statement, the same number on both sides, then it works. So that means that is the solution, right? All right, so let's try an example on our own. So it says we're watching a show in which people compete against each other to lose weight. The trainer exclaims, "Down 7 pounds in a week." On a screen behind the contestant, his current weight, 168 pounds. What was his weight last week, right? So the first thing I want to do is solve numerically. So if we think a minute about what's going on, we're taking your old weight, right? And the person lost 7 pounds, so we're subtracting 7 pounds. and then we're coming up with 168 pounds, right? That's what was on the screen after losing 7 pounds. So if I want to think about solving this numerically, I need to take the smaller weight, 168, and add in the weight that I lost, and this will give me, 175 pounds. That's my weight that the person was previously, right? So we can just solve that numerically. It says what operation was used. Well, we used addition, right? So then next we want to write an algebraic equation. So the first thing you want to do is, pick a variable and say what it means, right? So for example, we could use this W for weight. So we could say let W equal his weight last week. Right, so that's what W represents. So now I don't have to write down, what that means. I can just use W in that place instead of writing this whole phrase, right? So an equation is, W minus 7 equals 168, right? So kind of just using what we were thinking about over here, and we can turn it into an equation, right? So then part C is we want to actually solve this. So we have W minus 7 equals 168, just copying down the equation. And then so to be able to solve this is, notice I have a variable term on the left and a constant term, and then I have a constant term on the right of the equation. So I want to move this over here in a sense, right? I don't want this here, so I can get W by itself. So how do I undo subtracting 7? Well, I do the opposite operation, right? Add 7. Right, so if I add 7 to both sides, these cancel each other out, right? Because plus 7 minus 7 is just 0. So and of course 0 plus W is just W, right? So I'm left with just W on the left-hand side, and then 168 plus 7 gives me 175. Right, so I get the same solution as before, 175 pounds. And then we can check our work, right? So plug it in. So we take this and plug it in for W and see if we get the same result. So you take 175 minus 7, does that equal 168, right? So and this does equal 168, right? We get 168 on both sides. So it checks out, right? So it says check your work, and then it also says state the answer to the question, right? So you could say like his weight last week was 175 pounds, right? All right, so then this next blue box just says, how to solve a one-step equation. So, it's a little different than how I presented it, and if you find that easier, feel free to, follow along. It's just a different way to look at it. So I'll let you read that, and you can go through that if you'd like. All right, so then this next one, it says your email account states that 3.36 gigabytes, 21% of storage space has been used. How much storage space is allotted to your email account? All right, so this one maybe is kind of, I don't know, maybe kind of difficult. I think it's easier to do algebraically, but it can be easy to do numerically if you draw a picture and think about it like a meter, right? So I'll do that now. So if we think about the bottom being 0 gigabytes, right, and that being 0% of the storage, and then up at the very top of the meter, let's say that's 100%, right? So if it's all filled in all the way to the top, that's full, that's all of it, and that's what we're trying to figure out is how much total storage is there. So this would be the total gigabytes, and then what we know is somewhere, somewhere between 0 and 100%. Whoops, and I should have flipped these, right, so that way it's consistent. Sorry about that. Just to have the percents on the same side, so you could fix that in your notes if you wanted, right? Put the so make this 100%, and this be total gigabytes, right? So then this is what we've used, right? 3.36 gigabytes. And this corresponds to 21% of your storage, right? And I can fill this in. So that's how much of our meter is full, if you will, right? So then maybe a way to think about this is if I take a 3.36 and divide by 21, this will give me the amount of gigabytes in 1%, right? Because I use 3.36 gigabytes in 21%. So if I take that number, divide by 21, that would correlate to how many gigabytes there are in just 1%. And then if I know 1%, I can just multiply that times 100 to get 100%. Right? So let me go over to my calculator and take 3.36. Maybe we want to divide that by 21. So we get 0.16, right? So there's 0.16 gigabytes and 1% of our data storage, right, in our email account. So then to find 100%, if I take 0.16 times 100, this will tell me the number of gigabytes and 100%, right? So 0.16 times 100, right? I could use my calculator, but I don't need to, right? That's going to take the decimal and move it 2 spots to the right, right? So we get 16 gigabytes, right? So in terms of solving the problem numerically, right, what we did is took 3.36 divided by 21 and then multiplied it by 100, right, is what was done. And there we got 16 gigabytes. Right? So it says what operations was used, right? So some people might have used just division or something. We could have got away with that, but we actually used 2 operations, right? We use multiplication and division, right? So what I mean is if I would have taken 3.36 divided by 0.21, this would also get me my answer of 16 gigabytes, right? It's just another way to rewrite this, right? Basically, you're dividing the top and bottom by 100, so that way you're changing the decimal point in the bottom. But you didn't have to do that. I think doing it the way we did is easier, especially with thinking about this meter, if you will, right? The picture that we drew. All right. So then let me change color so we don't all run together. The next thing that we want to do is write an algebraic equation, right, for how to solve this. So, an algebraic equation that we could get is if we were to let, S equal the storage, of your email account, right? I don't know if we want to specify the total, right? The total storage of your email account. Then what we could do is if I take 21% of that, right, 0.21 times S, that's going to equal 3.36 gigabytes, right? And that's just the effect of percents, right? That's what this meaning is, right? 21% of our total storage space is equivalent to or equal to 3.36, right? So then part C, we want to solve this equation. So if we divide, right, because what's going on in between 0.21 and s is times, right? So if I divide both sides by 0.21, then I'll get s by itself. So, 0.21 divided by 0.21 is just 1s, right? So I can just write that as s. If you want to write 1s, you can, but that's the same thing as s, right? 1 times s is just s. So then if I take 3.36 divided by 0.21, whoops, I did 0.22, sorry. I meant to do 0.21. We get 16, right? Which is exactly what we got before, 16 gigabytes. Then, of course, we can check our work, right? So I can take 0.21, plug in 16, and see if this equals 3.36, right? So 0.21 times 16 is equal to 3.36. Oops. Right, so we get that solution. Okay. Let me just change this. All right. Right. So then you could state an answer to your question, right? You could say the total storage provided is 16 gigabytes, right, as an example. Right. So then number 4 is another one to try doing something similar. So it says you're reading the newspaper and see home value assessments. Your house is listed at $42,340. Assessments are 1/3 of the true value of home. What is your home actually worth? Right. So another strategy that you can do in mathematics is to give yourself like a simple example with some nice numbers and just to try to get an understanding of the problem, right? So let's try a simple example, right? So this number, notice, is not very round. So maybe, I don't know, maybe I'll just pick 50,000 for that, right? So in that number is the home value assessments, right? So this is the home value assessment, right? So it says assessments are 1/3 of the true value of your home. What's your home actually worth, right? So in other words, if you think about like kind of that bar kind of thing, right? If I cut this into thirds, right? So this is, 1 whole, right? 2/3, 1/3. So 1/3 of my home would be 50,000, 50K, right? And then so 2/3 would be 100,000 or 100K, right? And then 1 whole would be 150,000, right? So in other words, if we know 1/3, in order to find all the parts, we'd have to multiply by 3, right? Which makes sense because this is a smaller amount, and the actual home worth is 3 times that, right? So if your if your home value assessment was $2,000, then your home would actually be worth, I think I said 2,000. It would be worth 6,000, right? 2,000 times 3. So we just need to multiply by 3, right? And I guess I didn't spell this out very quickly, right? If you're unsure of like how I got 100 and 150, right? Just think about this as units, right? 50,000 is 1/3, so 2/3 is just, you're taking 50K and adding 50K to it, right? You're doubling, right? So you get 100,000, and then 3/3 is 1 more third, so I'd have to take 100 plus the 50, right, to get 150,000, right? So in terms of solving this numerically, right, now that we've kind of thought this through about what to do, I can just take my my home value assessment, which is $42,340, and multiply this times 3. Right? And that, so if I do that, so 42,340 times 3, we get $127,020. Right? So then part B is we want to be able to write an algebraic equation, right? So maybe you want to let V equal the true value of your house. Right? So then the equation that we could come up with is 1/3 of my value. 1/3 of my value is $42,340, right? And I forgot to answer this question. What operation was used? We used multiplication. Right? So then actually solving this equation, so just writing this equation down, I would want to divide both sides by 1/3, right, to get rid of this coefficient, make it 1. But dividing by 1/3 is the same thing as multiplying by 3, right? If I have 1/3 V divided by 1/3, that's the same thing as 1/3 V times 3 over 1, right? Because it's the same thing when you divide fractions, you multiply by the reciprocal, right? And 3 over 1 is just 3, right? So one thing I could do to solve this, hang on a moment. There you go. Sorry about that. I was getting a phone call from my son's school, but all right. So where were we? All right. So we were thinking about solving this equation. I was just telling you how we can just multiply both sides by 3, right? So if I multiply this side by 3 and I multiply this side by 3, then over here I'm going to get just V by itself, right? Because 3 times 1/3 is just 1, right? So it's just 1V, or V by itself. And then over here, I need to take the 42,340 times 3, which we already did and got this amount, right? So we're going to get the same amount again. So we get 127,020. Right? So that's the amount that we get. And of course, to check our work, right, we would take 1/3 times our answer, so plugging that in for V, 127,020, and we want that to equal 42,340, right? So just plugging this into that equation, and then, if I take 1/3 times 127,020, I get that amount, right? 42,340. Right, so it works out. We get the same number on both sides once we simplify. So therefore, that's a solution, right? Just a simple way to check and just verify we didn't make a mistake somewhere, right? And one thing, if you haven't noticed, the reason why this step is here is just to get us to think about, notice the step we use to solve the problem numerically is also the operation that we use to solve the equation, right? Or roughly speaking, right? The last time it didn't, what maybe wasn't quite as obvious because, we divided and multiplied, but I was showing you how you could do the whole thing with just dividing, which is what we did in the equation, right? So I think it's just trying to, help you understand that it's very similar, numerically and algebraically is very similar to each other. They're very related to get the same answer. Right? All right, so then there's another example in the text, and I'll let you read over that one and give it a try on your own. And then there's one more problem for us to do and try, so I want to go through that. So it says throughout this section we've solved one-step linear equations, right? So the 1-degree polynomials, right? So one step is just meaning we've only had to do one step in order to find a solution. And then we're told which are polynomial equations of a degree 1, right? So one-step equations can also contain a polynomial with a higher degree, such as x cubed equals 64. So it says whenever you choose to use algebra to solve a problem, you need to determine the operation done to the variable. Doing so allows you to determine the inverse operation that should be performed on both sides to isolate the variable. Right? So let me come off to the side here. So, if you have a polynomial, let's say we have polynomial p of x, then kind of a generic form of a polynomial is you have a sub n times x to the nth power plus, and then you'd have a to the n minus 1 to the x to the n minus 1 power, and then this pattern would continue, right, until we got to, let's say, a sub 2 x squared plus a sub 1 x to the, you can think about it as x to the first plus a sub 0 x to the 0 power, right? So this is a polynomial in generic form, right? And I emphasized a few things that you normally wouldn't, and we can fix that and correct that. But normally, for example, we wouldn't write x to the first power because that's just x, right? And then also we normally wouldn't write x to the 0 power because that's just 1, right? If you take, in most cases when you take a number raised to the 0 power, you get 1 back, right? There's one exception, right? The one exception is when x would be 0, but we could simplify that to be 1, right? So the general idea is that these a sub n, these parts, these are just coefficients, right? These are just constant numbers, and then you have times x raised to some power, right? And this it's written in a way where the first term is the biggest power, and then because this is n minus 1, and then you'd have n minus 2, and then n minus 3, all the way until you get to 2, and then 1 and 0, right? So the powers are getting smaller as we go through the line, right? So it's written in a way where n is referred to as your degree, right? So when you have a polynomial, your degree is just the biggest exponent for x, right? If you have just one variable. So what we've dealt with is just 1 degree polynomial so far, right? Where it's just x to the first, right? That's the only highest degree that we had. And then in this problem, we're going to work through some others, right? So again, I could rewrite this really quick. Just to simplify these two last parts that I highlighted. So normally you would just write a sub 1 times x plus a sub 0, right? So then this is just going to be a number, right, a constant. So there's no x in that term. And then something else to notice is, the reason why we have these subscripts, it might seem kind of scary, but it's just showing that they match, right? So a sub n matches with the degree n polynomial term, right? So n minus 1 matches this exponent, right? So notice the numbers match the exponent, and that's just to clarify, right? And we need to use those symbols in mathematics rather than using a every time, because when you use the same variable over, that represents that it's going to be the same value, and those aren't necessarily going to be the same, right? So the nice thing about using these n sub 1s is the exponents match, right? So the a sub n and a sub n minus 1, but also it's clear that a sub n is not necessarily the same as a sub n minus 1, right? They could be the same, but they're not necessarily the same, right? So you've probably seen that notation before, maybe in high school, maybe taking like an algebra class, right? So the big thing I want you to get out of that is just so you understand what a polynomial is and then what we mean by that degree, right? So in these next two, the first one, I believe we're doing a degree 2 polynomial, and then the part B, we're doing a degree 3 polynomial, right? So For part A, it says a homeowner has enough patio pavers to make 200 square foot patio. He wants the patio to be square. What will the dimensions of the patio be if he wants to use all the pavers? State your answer in feet, inches, such as 5 feet, 6 inches, right? So if you draw a picture real quick, to what's being asked is we have this square, right? And a square has the same side on both sides, right? So maybe, we let x equal the side of the square, right? So all around this, we have x's all around the patio, right? This is my patio. But I want the area of the patio to be 200 square feet, right? Because that's what I have enough pavers to make, right? So it says, what will the dimensions be if we want to use all the pavers, right? So we want to try to use all the pavers that we can, but how can we come up with a way to figure out what x would be essentially, right? What would be the dimensions? So if you think about how you find the area of a rectangle, right, you multiply length times width, right? Or in the case of the square, the length and width are the same length, right? The same distance. That's what makes it a square. So then you can just take one of the sides and square it, right? So in other words, the area is going to be equal to x squared, right? But also we know the area is 200 feet. So we can just put 200 in for A and make an equation. So we'd have 200 equals x squared, right? And then you want to think about how do you solve this, right? So let me just put a line here just to show these are separate, right? I maybe wrote that a little close. But how do we undo squaring? We undo squaring by square root, right? So I have to take the square root of both sides. So then x would equal the square root of 200, right? So then if I go to my calculator and take the square root of 200, we get this answer, right? Let me just put this back on the right side there. Right? So this actually turns out to be an irrational number, but this becomes approximately, 14.14 feet, right? That's our answer rounded to the nearest 2 decimal spots of feet, right? So 2 things before we're done with this problem. One is this is not the form that we wanted our answer to be in, right? What we want to be able to write feet and then inches, right? Be able to fill this in, right? So it's pretty easy that this 14 is just going to go here, right? I have 14 total feet, but this part, this 0.14 is actually more decimals to it. That number doesn't go just here, right? That's partial of a foot. So a technique we could do is take away 14 from our calculator and be just left with that decimal portion. And then if I take that and multiply by 12, that would convert it into inches, right? Because if you know feet and you multiply by 12, it'll turn into inches, right? So if I have like 3 feet and I multiply that by 12, I get 36. So there's 36 inches and 3 feet. So then what I would get here is 1.7 roughly, right? If I just round to 1 decimal spot. So 14 feet, 1.7 inches, or if you wanted to round to the nearest inch, right, we could just say 2 inches, right? We wouldn't quite have enough patio because we rounded up, but those are basically the dimensions that you would want to make that patio happen, right? So then another thing that I want to go over is this idea with solving this equation, right? This point, right? I want to talk about what it means to solve that, right? So let me come over here to some blank space, right? So we had x squared equals 200 and we were solving it, and we come up with x equals the square root of 200, which was approximately 14.14, right? That's just a reminder of what we did, but technically, that's right because of the context of our problem. But in general, this answer is partially right. It's not the full answer. And I'll show you what I mean by that. So if you think about squaring a positive number, right? So if I take a positive number, and let me just represent it with positive in parentheses. If I take a positive number and square it, right? That's a positive number times a positive number, which gives me a positive number, right? But then also, if I take a negative number and square it, that gives me a negative times a negative, which equals a positive number, right? So that's just to the second power. So one thing you want to notice is I don't know what the sign was originally after I square something, right? Because if I take a number and square it, I'm always going to get a positive number, right? If I'm squaring the whole number, there's nothing multiplied out in front or anything, right? So the number could have been positive or negative, right? And this is true anytime your exponent is even, right? So like if I take a positive number to the 100th power, that means there's going to be 100 positive signs, right? But since it's even, what that means is every odd or every positive guy is going to have a pair, right? So that means we're going to get a positive, right? Just multiply a bunch of positive numbers, you're going to get a positive. But similarly, if I take a negative and take it to the 100th power, right, we're going to have 100 of these negatives, but just like above, right? So it didn't really impact above because you're just taking a bunch of positives together. But when you take a bunch of negatives and multiply together, if you have an even number where they have a pair, then each pair cancels each other out, and you're left with just a bunch of positives being multiplied together, right? So you get positive, right? So in other words, if you have a negative number and you take it to an even power, then this is always going to be positive, right? But as you can imagine, if I take a negative number and I take it to an odd power, that's always going to give me a negative number. If I take a positive number to an odd power, that, of course, would be a positive number, right? So, for example, if I take a negative 3 cubed, right, this would be negative 3 times negative 3 times negative 3, right? This would equal, right, so these two negatives make a positive number, right? But then you have one negative out in front. So a negative times a positive is going to be a negative number, right? So I'm left with negative, so 3 times 3 times 3 is 27, right? So negative 27. Where if I take 3 cubed, we would get positive 27, right? Because it'd be 3 times 3 times 3, right? So the important part, the pattern you want to notice is when I take a number and raise it to an even power, the original so when I take a number raised to an even power, the original sign, if it's positive or negative, is lost, right, if you will. So if I take a number and square it, and I only tell you what I squared, I don't know if that answer originally was positive or negative, right? I don't know. It's lost, right? Where if it's an odd power, you don't you do know because the signs will always match, right? So if I take a negative number to an odd power, I always get a negative answer. If I take a positive number to an odd power, I always get a positive answer. So those signs always match, right? So my point is in general, if I have an equation like x squared equals 9, right? This is an even power. So remember, when I square something, I don't know if it was positive or negative to begin with. So the correct way notationally to do this is when you take an even root of both sides, then you have to put a plus or minus to one of the sides, right? So notice x, the square root of x squared is just x, right? They cancel each other out. And then on this side, I just put a plus or minus in front. And then we could simplify, what's the square root of 9? Well, that's 3, right? So we get plus or minus 3 as an answer, right? And what this means notationally is that x equals 3 or x equals negative 3, right? Plus or minus means it could be one or the other. So both answers would have to be true, right? But this problem that we were dealing with x, our variable, was the length of something, and you can't have negative length. So that's why this answer was true in the context of our problem, right? But in general, this answer would actually be plus or minus, but then given the context of our problem, we would throw out the negative solution, right? So it worked out for us, right? So that's just something to keep in mind when you're solving equations like that. Right. So let me go back to here. So we figured out A, okay, part A. So then part B is dealing with, we want to build a cube-shaped bin to hold compost, and it needs to have 5 cubic yards of compost, right? So I'm not very good at drawing in 3D, but we have a cube, is a 3-dimensional square. So it's, maybe if you ever play with blocks, right? You probably had like wooden blocks. That was like in a cube shape, right? Maybe they had numbers or letters written on it. So every dimension for a cube is going to be the same, right? So the volume for a cube is that you take the side and you cube it, right? Where S is the side length. So in this case, if we just plug in, right, we want 5 cubic yards, so that's the volume, and we want to figure out what would be the dimensions of this. So we'd have 5 equals x cubed, right? So then to undo this, we would have to take the cubed root of both sides. And remember, since we're taking an odd root, we don't have to worry about that plus or minus thing. It's only when this number is even, right? And when you do just square root, really there's a 2 here, right? So if you do the square root of x, that's the same thing as the square root, like 2 we use for square. That's what that's referring to, right? So we just normally don't write that 2 there. It's just understood that you're taking the second root. So then, but with the cubed root, we don't have to worry about the plus or minus business. So x would just be equal to the cubed root of 5, which we could plug in our calculator to solve. Yours might be found in a different spot, but I know for my graphing calculator, it's under math, right? So I have a cubed root. So in your calculator, you might have to use this option. You might have a blue button that has an X and a cube. So you would put in 3 first, and then hit that button, and then put what you're taking the cubed root of, or whatever root. Right. So I'm going to use that because we're doing the cubed root. So I went the cubed root of 5. So that gives me approximately 1.71 feet. No, these are yards. Excuse me. The dimensions is cubic yards, so what would be left is yards. Right? So then what we want is the dimensions in feet and inches, right? So I want to have a blank with feet and a blank with inches. So an easy thing to do is I could take this 1 yard and put it here, right? So that's 1 yard. Bring it over here. That would be 3 feet. Right, so I could write 3 feet here, right, instead of the 1 yard. But then what I have next is I have this 0.71 yards, roughly, right? I want to convert this into inches, right? So what I'm going to have to do is take this and multiply by 36, right? Because there's 36 inches in a yard, right? Because there's 3 feet in a yard, and there's 12 inches in every foot, so 3 times 12 is 36, right? So over here, like if I take away 1, that'll leave me with just the decimal part, and then I can multiply by 36, and now my answer would be in inches, right? So I would have roughly, we'll say 26 inches, right? But this is kind of awkward way to write this, right? 3 feet and 26 inches. So what's awkward is that this is bigger than 12, right? Because if this is bigger than 12, no, we want this to be less than 12. If this is bigger than 12, then I can take, some over here and make more feet, right? So let me get some white space to finish this problem. All right, so we had, 3 feet, 26 inches. So if I take away 12 inches. That would be like adding 1 foot over here, right? So if I did that, that would give me 4 feet. So 26 minus 12 would be what? 14 inches. And then I could take away 12 inches again, bring it over here. That's like adding 1 foot over here, right? If I just transfer those, that would be 5 feet. And then 14 minus 12 is 2 inches left, right? And that would be the answer, right? So each dimension should be roughly 5 feet, 2 inches, all right? All right, thanks. So that hopefully that helped get you through the notes. And don't forget, if you have questions, there's tutoring on campus, and I think it's available from 11 to 2 Monday through Thursday in Bryson Hall in the Academic Success Center. All right, thanks.